Hello and welcome to the class of Econometrics 2, Econ 333. My name is Yasser Saeed and today we are going with lecture number 15, that is on the Dickey-Fuller and Augmented Dickey-Fuller test. So in today's lecture, basically we are focusing on testing for the stationarity and unit root. And for that purpose, there are three tests that we will study today. There are many tests, but what we will cover here in this course, these are the three tests. The first one is the Dickey-Fuller test. Then the second test, we are going to make some changes in the Dickey-Fuller test, and that is called the Augmented Dickey-Fuller test. Then finally, a third variation of the Dickey-Fuller test, that is called the Phillips-Perron test. Again, these three tests are very identical and use basically the same equation, but a little bit of variations in them. So let's start with our lecture today. Alright, so we want to test for the unit root, and in order to do that, we may also test for the order of integration. Basically, these two processes are somewhat identical. So a test for the order of integration is a test for the number of unit roots and follow these steps. So let me write these steps in a very brief way. If we want to test for order of the integration, let me complete this writing. Then when we want to test for the order of integration, we follow basically these three steps. Let me call the first step step A. So in the first step, what we do is that we test yt to see if it is stationary, and if it is stationary, then we say that yt is integrated of order 1. And if we found that there is a unit root in it, then we will like to go to another step and see if it is integrated of order 2. So in order to see if the series is integrated of order 2, it must have of order 1 first. The first option is of integration 0. The second one, when we have when we take the first difference delta yt, and this is and we do not find any unit root after taking the difference, then we can say that y is integrated of order 1. And again, if we found a unit root after taking the difference, then we have a third step, and we take another difference of yt, and we call it that delta square yt, and see if it is integrated of order 2 or not. We check for the unit root. If we found any unit root, then it is not integrated of order 2. Otherwise, we can safely say that this is integrated of order 2. So this is the process, and usually we get the data. We can remove the unit root after first difference or after the second difference. So basically these two steps are usually required. If still we fail to make the data stationary, then this process might not be that much helpful. Anyhow, we want to find whether the data has unit root. How we know if the data has unit root? So for that purpose, we use a Dickey-Fuller test, as I've written here. We may also call it the DF test. So what is Dickey-Fuller test? It is a test that was devised in 1979. It is a formal procedure to test for the non-stationarity. The key insight of their test is that testing for a non-stationary is equivalent to testing for the existence of a unit root. Thus, the obvious test is following, which is based on the simple AR1 model, and we can use the AR1 procedure for testing such type of unit root. So we can write the AR1 process as YT, and we make that equal to theta YT minus 1. This is our you can say the AR process plus the UT. UT is the error term that we have taken in this model. What we need to examine here, that if the value of this theta, this equals to 1, then what happens? We have a unit root. If theta is not equal to 1, then we do not have any unit root. So basically the null hypothesis for testing this model then becomes that h naught is that theta is equal to 1, and the alternate hypothesis will be that h1 that is not equal, that is less than equal to 1. And why less than equal to 1? Because if it is greater than 1, again there is a unit root. This is an explosive series if it has a value greater than 1, but less than 1 means that the data remains stationary. So we test for these hypotheses and we can judge whether it has a unit root or not. But we have also an alternate method for it. Let me say that the first is equation 1, and we can rewrite this equation by taking the difference of yt with yt minus 1. Similarly, I will get theta minus 1 on the right hand side and multiplied that by yt minus 1 plus ut. So what I have done here is just taken the difference. So the first part, the left hand side, that will equal to delta yt, and we know that this makes the data somehow stationary. Now this will we will get theta minus 1 yt minus 1 plus ut. Again rewriting this and replacing the theta minus 1 element, we can say that delta yt is equal to, and replace that by gamma yt minus 1 plus ut. This becomes our third form. Now this is what the Dickey-Fuller equation basically use. If gamma value is equal to 0, then it is equivalent to the statement, because when we subtract 1, when the value of theta is 1, there is a unit root, then the value of gamma will automatically equal to 0. So the null hypothesis here is now different. The null hypothesis here is that gamma is equal to 0, whereas the alternate hypothesis will be that gamma that is less than 0. So these are the two hypotheses. Now the DF test will have to check, and if we found that gamma equals to 0, then YT follows a pure random walk model with mean 0, and YT will equal to change in YT will entirely equal to random variation, the stochastic term UT. So that is a pure random model. Then Dickey-Fuller in 1979 also proposed two alternative regressions equation that can be used for testing the presence of unit root. And the first contains a constant in the random walk process, and that equation we can write the equation as let me write that equation here, delta yt, and this delta yt will now equals to alpha naught. This alpha naught is basically the constant term that we have introduced into our model, plus gamma yt minus 1. Gamma, again gamma yt minus 1 is basically the same equation with gamma's value equal to 0, and ut is the error term. So this is an extremely important case because the process also exhibits a definite trend in the series when gamma equal to 0, and we can show this trend because when you put gamma equal to 0, you are left with delta yt is equal to alpha naught. Let me rewrite this. If gamma equals to 0, what we are left with is alpha naught plus uh, yt plus ut. So yt into gamma basically is 0, and this alpha naught is a constant term, so we see the change in yt is constant, plus there is some random variation, and we can also graph this. There is a consistent increase but with certain variation. So if we want to see this graphically, uh, here you see the graph trends upward. It has a continuous trend, but there is also a random variation involved in the data. Now, what happens when we put alpha naught equal to 0? When alpha naught is equal to 0, then in that case, we have uh, the change in yt equals to a random variation ut. So the change in yt then becomes entirely a random variation, and that is not predicted, and it has a mean of 0, as we know that ut has a mean of 0 and it has a constant variation. But this variation, that this is stochastic, this is random and is not predictable. So this is how the two equations would look like in a graph. Then there is also a third form that Dickey-Fuller has used, and that third form involves a time trend. And we can also show the time trend by adding another element, that is alpha 2 into time, right? So you see the first equation, we have discussed it. We rewrite the first equation or the second equation by adding this time variation. Let me write it here. This is the change in yt, and this change in yt equals to alpha naught. This is the already constant term that we have introduced, but the next is the alpha 2t. Alpha 2t basically represents the variation due to time, and the remaining of the equation is exactly the same, plus gamma yt minus 1 and plus ut. So the df test for the stationarity is then simply the normal t test, and when we do the normal t test, we will test for the coefficient of the lag dependent variable, and that lag dependent variable is yt minus 1. So from one of the three models, we will use the process similar to the t test. The test does not, however, have a conventional t distribution, and so we must use a special critical value that was originally calculated by the Dickey and Fuller. Also, the McKinnon in 1991 tabulated appropriate critical values for each of the three models. And in all these three cases, the test focuses on whether the value of gamma equal to 0 or not. And the DF test statistics is the t statistics for the lag dependent variable. If the DF statistical value is smaller than the critical value, then the null hypothesis of a unit root is rejected, and we can conclude that the yt is a stationary process. The only difference here, that from the typical t test, is that we use different critical values other than the normal t critical values that we are used to. Then we also want to introduce the augmented Dickey-Fuller. Let me write that: augmented Dickey-Fuller test. And we also write a shorter version for this, by which it is usually known, that is the ADF test for unit root. Now, let me describe the ADF test, the procedure, why it is required. As the error term is unlikely to be white noise, typically in a time series data, we have autocorrelation. So the error term is not likely to be a white noise. Dickey and Fuller extend their test procedure by suggesting an augmented version of this test that includes extra terms of the extra leg terms of this dependent variable in order to eliminate autocorrelation, and the leg length of these extra term is either determined by the Achic information criteria or the Schwarz-Basin criteria, also known as the AIC or the SVC values, or more usefully by the leg length necessary to whiten the results. That is, after each case, we check whether the residual of the ADF regression are autocorrelated or not through the LM test rather than the Durbin-Watson test. So again, we have three possible cases, the same cases, but what we now want to change here is the that instead of simple yt minus 1, we also introduce the leg terms with it, and these leg terms can be written as delta yt is equal to gamma yt minus 1 plus summation, and the value then we have summation bi, the delta yt minus I yt minus I, and the value of I is from 1 up to p, so it can have any number of leg lengths that we require. Then we add the error term ut. So this is the first version of the augmented Dickey-Fuller equation. Then again, it does not involve any constant, so if you want to add constant to it, what we do, we rewrite the equation as delta yt is equal to alpha naught plus gamma yt minus 1, and the remaining of the equation is very much identical to the equation number 1, the first ADF equation that we have written. So this becomes our second equation that involves the constant term, and we may number it the summation as I from 1 to p, and same is true for the first equation as well. So this is our second equation, and the third equation will now involve the time trend, and we can write the time trend as delta yt equals to alpha naught plus gamma yt minus 1 and plus alpha 2 t. This is the time factor that we have added to the equation, and again the rest of the equation is very much identical to the one that we have written in the above two cases. And now we introduce the leg terms with beta I, and change in the dependent variable yt and yt minus I plus ut. Forgive me for the miswriting, because the pen doesn't work on certain areas of the laptop. Anyhow, do remember that this is delta yt minus 1. So the difference between these three regressions again concerns the presence of the deterministic element of the alpha naught and alpha 2t, and the critical values for the ADF test are the same as those given for the Dickey-Fuller test. These both are identical. Unless an econometrician knows the actual data generating process, there is a question concerning whether it is most appropriate to estimate equation 1, equation 2, or equation 3. But anyhow, there are certain you say econometricians like Doldado et al. 1992, who suggest the process to start with the third equation and then start eliminating the certain equation within the model. And they have a procedure. Even we have another procedure that was developed by Anders in 1995 for testing the unit root, and that can be seen in another graph if you want to aid, but I do not have that graph here, which estimates the model first and then see if the entire model, and then see if there is gamma equal to 0 or not, and then in the next step try to reduce some of the components. Then there is a third version to the model that we call the Phillips-Perron PP test. Uh, Let me write it. Phillips-Perron test, or also known as the PP test. This is basically very much identical to the earlier two tests that we have conducted. The distribution theory supporting the DF and the ADF test is based on the assumption that the error terms are statistically independent and have a constant variance. So when using the ADF methodology, one has to make sure that the error terms are uncorrelated, and they really have to have a constant variance. But Phillips and Perron in 1988 developed a generalization of the ADF model, and that used the same assumption of the distribution, and using the same equation as in the AR1 process. For the Phillips-Perron test, delta yt minus 1 equals to alpha naught plus gamma yt minus 1 plus the error term. Now this error term might be serially correlated, while the ADF test corrects for the higher order serial correlation by adding the lag difference terms at the right hand side. The Phillips-Perron test is basically of the coefficient gamma from the AR1 regression to account for the serial correlation. So the Phillips-Perron statistics are only modification of the ADF-T statistics, and take into account less restrictive nature of the error process. So the expressions are extremely complex to derive, and they are beyond the scope of this lecture. However, since many statistical packages like eViews do use such types of eViews do use such type of tests, so we do conduct these tests alongside with the DF and ADF test. It is better to use multiple tests for a unit root, and since softwares help us calculate them, we should use these softwares, and with the help of them we should calculate the Phillips-Perron test. So that's all about today's lecture. In the next lecture, what we are going to do is we will see how to check the Phillips-Perron, the DF and the ADF on the eViews, how we can check for the unit root over there. Thank you very much, and thanks for watching these lectures.